What's up, folks? It is Saturday morning. I'm in Nebraska. I'm hiding out in my grandparents' basement because I am neglecting them so that I can talk to you all about implicit differentiation. That's what we're talking about today. So let's go ahead and get started. Quick do now for you. I want you to find dy dx given this function. Now remember, dy dx is saying that we are talking about a derivative, and you should recognize this form of a function as a conic section. You should recognize this as the equation of a vertically opening parabola. Now, quick reminder before I ask you to pause this video and do this problem. Before you can take the derivative of this function, you need to solve this for y. So FOIL out your x terms and then solve for y. And then use the power rule for derivatives to take the derivative. So remember the power rule for derivatives, if I had x squared, for example, I would get 2x. You multiply the power by the coefficient and then subtract 1 from the power. So please pause the video now, and I want you to take 4 minutes, no longer, 4 minutes to find the derivative of this function. So pause 4 minutes, and then we'll run through a quick explanation. Pause. Alright, so hopefully you've found your own derivative for this function, dy dx, y prime, whatever you want to refer to it as. I'm going to do a quick walk through this and then we'll go. So let's go ahead and FOIL the right side of this out, expand it, figure out what this is, not as a completed square. So we're going to get x squared, our x times x, plus 4x plus 4 when you expand that. On the left side, I'll still have what I had before. And now, again, we're trying to solve for y. So let's divide everything by 6. And what I'm going to do is I'm going to write this as y minus 4 equals, I'm going to just write it as 1/6 times x squared plus 4/6 x plus 4/6. I can simplify stuff later. That should work for me for now. And then I'm going to add 4 to both sides, so I'll have my 1/6 x squared plus 4/6. I'm going to go ahead and write that as 2/3 x plus 2/3, and now plus 4. So now that I've solved this equation for y, I can go ahead and take the derivative. Now, what happens to the left side of this equation when I take a derivative? Well, y becomes y prime, or we can just write that as dy dx, the derivative of y with respect to x. So anytime you have a y term like that, you'll always end up with a dy dx there. Now my first x term, x squared with the coefficient of 1/6, I need to multiply the 1/6 by that power. So the 2 times 1/6 becomes 2/6, which is 1/3, and the x squared becomes x, because you subtract 1 from the power. And then my next term is a 2/3 x. Well, my power there is 1, so I multiply 1, and I get my positive 2/3. And then I subtract 1 from my power, which means my x to the first becomes an x to a 0, which is just a constant term. Then I have my 2/3, and remember, anytime you take the derivative of a constant term, you just get 0, so that just goes away. And so I end up with the derivative of my function as 1/3 x plus 2/3. dy dx equals 1/3 x plus 2/3. So hopefully you ended up with that as well. We're going to take this a little farther and see how we can handle implicitly defined functions in addition to explicitly defined functions. That's our objectives for today. Take derivatives of implicitly defined functions. But we need to talk about what an explicit versus an implicit function actually is. So an explicit function is basically what you would probably think of as a, quote, normal function. It's a function that is defined explicitly in terms of y as a function of x. So for example, when you have a function as y equals, and then on the other side of the equal sign you only have x's and just constant terms, that is an explicitly defined function. Y is a function of x. And so we could even think of it as y equals some f of x function, where f of x function is that 3x plus 2. Now, I could write the same exact relation there, that y equals 3x plus 2. I could write that as an implicitly defined function. Notice it's the same thing. If I wanted to, I could move that 3x over and I would get back to where I am right there. But now it is not explicitly solved for y. Now sometimes you can take an implicit function and solve it for y and write it explicitly, but you can't always do so. If you think about the conic sections that we're dealing with, some of these conic sections end up with y squared terms. And so we can't solve them explicitly for y without having a plus or minus of some square root stuff. And that isn't technically explicitly defined as just a single function. So we still want to know how to take derivatives of implicit functions, derivatives of conic sections, because that can tell us many useful things about the conic sections. But we need to think about another way to do so. So again, let's just hit it real quick. How do you find a derivative explicitly? Well, your y becomes a dy dx, the derivative of y with respect to the derivative of x. It's the same as saying y prime. If I wanted to, I could say y prime equals this. But then the power rule says multiply the power by the coefficient. So 4 times 3 is 12. Subtract 1 from the power, so we get 3 minus 4x becomes 4, and your constant term goes away. But the key thing I want you to think about right now is when you take the derivative of a y term, you get this dy dx. So if I want to go and take the derivative of this function implicitly, I can go ahead and do the same thing. And notice I have the same function here. If you look at those terms and these terms, they're all the same, but it's no longer defined explicitly because it is not solved for y. But I can go through and I can say, all right, I want to take the derivative of the left side of this equation, and I also want to take the derivative of the right side of this equation. So the derivative with respect to x of y is just going to be my dy dx minus the derivative of 3x to the fourth is going to give me 4 times 3, again, is going to give me that 12x, drop the power by 1, cubed, plus my 4 from the 4x term there, equals the derivative on the right-hand side. Well, that's just a constant term, so the derivative of a constant term is always 0. And so I get this expression right here, which looks pretty similar to what we have over here. We have a dy dx, a 12x cubed, and 4, but everything is on different sides. And so I could rearrange this equation. I could add 12x cubed and subtract 4 from both sides to get dy dx equals my positive 12x cubed minus 4, which is the same derivative I found explicitly. I just found that derivative implicitly as well. And so you should find the same exact derivative explicitly or implicitly, but we're now going to see how we can take more complicated derivatives using this idea of implicit differentiation. So I want to hit you again with this big idea. When you are differentiating a y term, let's put maybe quotes around that, a y term, you just use the power rule, and then you can think of it as multiplying by a dy dx or a y prime. What I mean by that is, imagine we had some function like this. Let's say we had y squared equals x as a function, and I wanted to know what the derivative with respect to x was of this function. Well, I take the derivative on the left with respect to x, and I take the derivative on the right with respect to x, and we can look and see what happens. It gets a little complicated because of that y squared term, but we have a way we can handle it. It's going to use something called the chain rule, which we have not learned in this class. You will get very deep into understanding the chain rule next year in calculus. But for now, what I'm about to show you will be enough for you to at least understand this process a little bit better. So let's pretend like we were taking the derivative of y squared with respect to y. Well, what would we get? Well, the power rule would say take that power and multiply by the coefficient. So we'd get a 2y, and then we'd drop the power by 1, making it just a y term. But the problem is we're not taking the derivative with respect to with respect to y. We're taking the derivative with respect to x. And so this is where that thing, the chain rule, comes into play. And what I want you to think of this as is anytime you differentiate a y term, you need to then multiply by the derivative of y, which we know as dy dx. So think about what I did real quick. Y squared went to 2y, just like an x squared would go to 2x. The only difference is I'm now multiplying by the derivative of y with respect to x. So on the left, I get that 2y times dy dx. And then on the right, we know the derivative of x with respect to x is just 1. And so now I have this expression here which includes this dy dx in there, which I'm interested in. That is the derivative of y with respect to x. But I want to solve that for dy dx. So I need to divide both sides by 2y. And so I can do that because this is an equation, divide both sides, and I get dy dx, my derivative of y with respect to x, equals 1 over 2y. And so again, I'm going to say it one more time. That is the big idea. Normal differentiation applies. The only difference is if you're differentiating a y term, you must multiply by the derivative of y, dy dx. Or if you want to use y primes, that's fine as well. So let's go ahead and look at an example now. I will do one. We'll walk you through it, and then I will ask you to pause and do your own. So let's find this derivative implicitly. So well, we're going to take the derivative on the left. And so the derivative of y squared, I'm going to use the power rule, and I will get my 2y times dy dx plus the derivative of 3x squared with respect to x. That's an ugly plus. It's just going to be 2 times 3 is my 6x. X squared goes to x. So 6x minus the derivative of x is 1. The derivative of 5 is 0, and the derivative of 0 is 0. So now I have implicitly differentiated this function, and now I want to solve for dy dx. So let's think about what I need to do. Well, first I have my 2y dy dx. I'm going to move that 6x and that minus 1 to the right side. So I'm going to get equals 1 minus 6x. So I've added 6x, and I've added 1 and I've subtracted 6x. So I almost have dy dx by itself now. What do I have to do? Well, I need to divide by 2y, because that is multiplied by my dy dx. So I have dy dx equals 1 minus 6x over 2y. And that is my derivative. And this is weird because the derivative is now defined in terms of both x and y. But if you think about it, y squared and an x squared term, we're dealing with some form of a conic section here, which means it's not an explicitly defined function. It would not pass the vertical line test. And so, if you look at some random x value, it's going to have two corresponding y values. And so in order to know which derivative we want, which slope of the tangent line we want, we also need to know what is that y value, which is why our derivative is defined in terms of both x and y. So now I'd like you to pause the video, and I want each of you to find the derivative of this function right here, 5y squared minus 2x squared plus 8 equals 0. Find dy dx for this function. Let's pause, and again, let's go like 3.5 minutes on this one. Try to find an answer yourself, and then watch my explanation. Alright, so hopefully you have found a derivative, dy dx, for this. Let's go ahead and take a look at it together. 5y squared is going to become 10y. And this time, let's say, instead of writing dy dx, let's write y prime, because they mean the same thing. So, 10y, y prime, minus 2 times 2 is 4x. The 8 goes away. Derivative of constant term is 0. So I get equals 0 right there. And I need to solve for my y prime. So I need to add 4x to both sides. So I have 10y y prime equals a positive 4x, and then I can divide by 10y on both sides to get y prime equals 4x over 10y, which I can simplify. Y prime equals 4 over 10 is the same as 2x over 5y. And so that there is my derivative. And again, it's telling me the slope of my function at whatever xy point I choose. Notice it's no longer just at whatever x value, it is at whatever xy coordinate you choose, because again, most x values will have two corresponding y values, two different points. So you need a full ordered pair to find actual tangent lines to conic sections. So there you go. Go ahead and try this one as well. Notice this is going to be a little different because this time we have two different y terms, which means when we take those derivatives, we're going to end up with two different y primes. So when you're solving, you're going to need to factor and get that dy dx, get that y prime out of those two terms, and then get it by itself. So again, your goal is the same, to get dy dx by itself, but you're going to have a little bit more complicated algebra this time. So please pause, and this time let's go 4.5 minutes, and pause and try to find this derivative, and then we'll look at a solution together. Okay, so let's go ahead and differentiate all the pieces of this function with respect to x. So 4x squared will become 2 times 4 is 8x, minus 2x becomes 2, minus 3y squared is going to become 6y times dy dx, plus 2y is going to become 2 dy dx. Think about why that happens. Again, the 2x became a 2, and the 2y became a 2, but then also that dy dx, because it's a y term. Negative 10 goes to 0, and so we just get equals 0, because again, the derivative of 0 is 0. So now, again, our goal is to solve this for dy dx. And so we need to move all our non-dy dx terms to the other side. So we're going to want to move this stuff over. So we're going to end up with negative 6y dy dx plus 2 dy dx equals, I'm going to add 2 and subtract that 8x just like that. And now, if you look at the left side, both of these terms have a dy dx in them, which means I can factor that out. So I'm going to pull my dy dx out front, and what am I left with in my first term? I'm left with negative 6y. What am I left with in my second term? I'm left with that 2. And so then that still equals this right-hand side, 2 minus 8x. So the last step to get dy dx by itself is divide by that entire expression, negative 6y plus 2. And so I'm going to do that. I'm literally going to write dy dx equals 2 minus 8x over 2 minus 6y. I rearranged that a little bit to make it look a little nicer, but that's it. And we can simplify this a little bit. All of these have multiples of 2 that we could divide out. So I'm going to say dy over dx equals 1 minus 4x over 1 minus 3y. Hopefully you can see how those two expressions are the same, but that there is my derivative. So the process works exactly the same, except when you have multiple y terms, you will get multiple dy dx's, and you will then need to factor and then divide out to solve for dy dx. And so I have one more for you to do, try by yourself, before I then give you a few problems to do for homework. Alright, so take a look at that equation on the left. You should acknowledge that that is the equation of a horizontally oriented ellipse. You should be able to identify the center. You should be able to identify the length of the major axis, the length of the minor axis. You should be able to graph this thing. You should be able to identify the coordinates of the foci. You should be able to do all of that stuff. And now I'm going to be expecting you to be able to find the derivative of this function as well, which would then allow you to find tangent lines of this function as well, which is pretty advanced mathematics. So kudos for you to you for being able to do that. You are very, very smart, and you are a very, very hard worker. So let's do this problem. But what do we need to do before we can actually take the derivative here? You're right. Just like in that very first problem we did, we need to expand everything. So let's do expand everything, and we'll then see where it gets us. Now, I'm a little, I don't know, how do I want to say this? I'm a little hesitant about those fractions, so I kind of want to get rid of them. I don't know, maybe we'll do that in a minute. For now, maybe let's just FOIL everything out. So x minus 3 quantity squared, that's going to become x squared minus 6x plus 9, so then we have that over 9, plus my y minus 1 squared is going to become y squared minus 2y plus 1, and all that's over 4. And this is all still equal to 1 right there. You know, a couple different ways we could handle this. We could distribute that 9 into each of those. Let's just get rid of it. So think about what we could multiply that would get rid of both of these denominators. Well, I think the easiest thing would be just to think of 9 times 4 is 36. So let's multiply everything by 36. So if I multiply everything by 36, this is going to simplify a little bit. Multiply this side by 36 as well. 36 divided by 9 is 4, and so we're going to end up with 4x squared minus 24x plus 36. Plus, my 36 divided by 4 is 9, so I will get 9y squared minus 18y plus 9 equals 36. And now that I have it written fully expanded like that, I can go ahead and use the power rule and implicitly differentiate this function. So let's do that. The derivative of 4x squared is 8x minus the derivative of 24x is 24. The constant term 36 goes away, so then I'll be left with plus my 9y squared will go to 18y times dy dx minus 18y will go to 18 times dy dx, and then the 9 is a constant term, so that derivative is 0, equals the derivative of 36 is 0. So now I need to get all of my dy dx terms on one side, everything else to the other side, so I can factor it and then divide. So let's say dy over dx factored out of, look at what I'm going to do. I'm looking at these terms right here. I'm factoring that dy dx out of that 18y dy dx, which means I'm left with 18y, minus I'm factoring the dy dx out of that 18 dy dx, so I'm left with that 18. And then I want to move the other stuff over. So I want to add 24, and I want to subtract 8x. So now I'm almost there. I just need to divide by 18y minus 18. So doing so, I can write this as dy dx, the derivative of y with respect to x, equals 24 minus 8x divided by 18y minus 18. And as I did before, I can simplify this. 24, 8, 18, and 18, they're all even numbers, which means I can divide them all by 2 to simplify this fraction a little bit. So I'm going to rewrite that as 12 minus 4x over 9y minus 9. And so that is what I'm going to say is my derivative. You can write it dy dx, you can write it y prime, but we know it equals 12 minus 4x divided by 9y minus 9. And again, this is telling me if I know any point on this graph, any ordered pair, x comma y, I can plug it into this derivative function and actually calculate the slope of the tangent line. So that is implicit differentiation in a nutshell. what I would like you to do is these 3 problems. You should hopefully still have a little time left in class. I want you to find the derivative of each of these functions with respect to x using implicit differentiation. The first one you should recognize as a horizontal parabola, the second one you should see as an ellipse, and the third one you should recognize as a kind of goofy hyperbola thingy because of the minus in front of the y term. So, expand each of these pieces and then use implicit differentiation to find the derivatives. We will check back up on this stuff on Tuesday and life will be good. We'll look at taking some tangent lines on Tuesday, doing some work with hyperbolas, and then we'll move forward to parametrics on Wednesday. So there you have it. 3 problems here to do, and then also 2 problems from your learning guide, numbers 9 and 10. Hopefully these things won't take you too long. You should have a little bit of time left in class to work through these. So please have these as well as all of the other problems from your learning guide that I've assigned, 1 through 4 and 6 through 8. So 1 through 4, 6 through 8, 9, and 10, and these 3 problems, I will be checking all of that on Tuesday. So get that completed. Come in with questions, but you got to at least give it a shot. So I will see you then, and have a great remainder of your day.